All right, so we're live here with 52 weeks of AWS. I'm continuing to cover the AWS Solutions Architect material. I'm almost done. I'm on the module 12, building decoupled architectures today, which is a fun topic. And after that, I believe there will only be three more sections to cover, and then I'll move on to something else. Maybe a little bit of coding and talk about some techniques with coding to take a little bit of a break. But one thing I'll announce here is that, and I'll just go ahead and share my screen here so I can talk about it, is that I do have a new course that's available on LinkedIn Learning that covers the AWS Certified Solutions Architect Professional exam. So even if you're studying for the regular Solutions Architect exam or Cloud Practitioner exam, this I think is a great course to really get you up to speed. And if you have access to LinkedIn Learning, you're welcome to take it. There are 5 different domains. So I put a lot of work into this course. If you want to get better at AWS, this is a great course to take a look at. So you just go to LinkedIn Learning and look for AWS Certified Solutions Architect Professional, and you should see the 5 different domains that I cover. Okay, that's the housekeeping. The next thing that I'm going to do then is switch over to the slides and talk a little bit about this topic of building decoupled architecture. Let's go ahead and get started here. And start with a few things to be aware of are that the tightly coupled architecture has actually been around for a long time. And in fact, in the early 2000s, there was a period of time where web frameworks were really a big deal. Ruby on Rails, Django, all those kinds of technologies. And what they really kind of promoted and actually made as their essentially their value proposition is that they are tightly coupled uh, monolithic systems. So they they tried to say that they're loosely coupled, but in practice they were tightly coupled systems because they were designed for the era before cloud computing really became a thing. And so they were non-cloud native systems. So traditional components have really tightly integrated components, and the object relational mapper is a perfect example of a tightly coupled component. It assumes that everything is on one machine with a database, and you're basically translating SQL to JSON and kind of going back and forth here. But in this particular example here, you can see there's Amazon Route 53, and it talks to a web tier, application tier, and database tier. The components are actually tightly coupled. Even though web frameworks will claim they're loosely coupled, this is exactly what a tightly coupled architecture is. This is a monolithic system. So if one of the parts of the application failed, like the database, then the whole thing fails. So tightly coupled architectures, one of the problems is that they impede scaling. So as you add more and more resources, it increases the complexity and it causes scale issues. And so this is really why cloud native systems are superior to traditional web frameworks. So what are some examples of system coupling? Application level coupling, for example, is relating to managing incoming and outgoing dependencies. Platform coupling is the interop of heterogeneous system components. Spatial coupling is relating to the managing of components at a network topology level or protocol level. And then temporal or runtime coupling is referring to the ability of a system component to do meaningful work while it performs asynchronous or blocking functions, right? So these are some great examples of tightly coupled theoretical concepts. Now, loosely coupled architecture is very different because there are intermediate components of them. And so this is, again, in reference to web frameworks that claim that they're loosely coupled but are not. Why they're not loosely coupled is they're not actually designed into the cloud in an elastic manner. So here's a great example. In this loosely coupled system, the elastic load balancer itself is distributing the traffic to a web tier, right? So it's you're basically designing, assuming that each of these individual components will fail. And potentially you also have an elastic load balancer going to an application tier, and then you also have a database tier. So each of the managed solutions that you really don't have to go through and orchestrate is being managed by the cloud provider. So this is a great example of the problems that get solved by cloud native systems. Some things to consider is that one potential point of vulnerability is saving the data to a database. So for example, if the business requires that the ordered data is going to be persisted, then there's different kinds of scenarios like deadlocks, race conditions, or network issues that could cause the persistence of the order to fail. And in this case, the order would be lost and you can't restore it. So that's definitely something to be aware of as well. So it's not like it's a silver bullet, but it does solve many of the problems that tightly coupled web frameworks introduce. Okay, let's talk about how you could architect something with SQS. So this is yet another example of how cloud native systems are uniquely different than these traditional kind of data center legacy systems. A message queue here is built for a decoupling architecture. There's a producer. This is an application that produces messages and adds them to a queue. There's a consumer. The application component then pulls the queue for the message and processes them. And the message is for communication of the software components, not for individual people, right? Like this is basically a way of decoupling the system so that the queue itself is basically causing communication between different parts of the system architecture. And in particular, I'm a huge fan of Amazon SQS because it has essentially infinite scale. And so, it allows you to decouple applications so they can run independently. It lets, let's say, a web service queue up messages that are generated by one application. So your web service isn't like tightly coupled with some other queuing system. The queue is a temporary repository for messages that are waiting to be processed. The messages are then stored until they're processed and deleted. And they can contain up to 256 kilobytes of text. And it can be in any format. And also, the SQS system is really at a massive scale that you could never create yourself, and it processes billions of messages a day. And the messages and queues are all within a single highly available region with multiple availability zones. So just as a recap here, a region is a geographic area, and a availability zone is a segment of that region that is potentially often more than one data center. And so you're really getting a highly available architecture with SQS. There's no single computer network or AZ that failure can make messages inaccessible, and they can actually be read essentially concurrently. And you can share the queue securely, anonymously, or with specific accounts. And they have high-level encryption methods. And also the SQS will support multiple producers and consumers interacting with the same queue. And SQS also has tight integration with EC2, S3, ECS, which is the Elastic Container Service, AWS Lambda, and DynamoDB. And in fact, one of the patterns that I like to use quite a bit is that I have a Lambda function listening to a queue, and you can do a one-to-one operation where if you're getting, let's say, thousands of messages per second, or tens of thousands, or 100,000 messages per second, whatever it is you need to do for your scale, you could have a one-to-one relationship with a Lambda, where each time it fires off the Lambda function, which then processes the message, then deletes it from the queue. That would be a great pattern to use for SQS. So you can achieve loose coupling with Amazon SQS because you can asynchronously process the responses from each step very quickly. You can handle the performance and service requirements by increasing the number of job instances. And also you can recover from failure because the messages always are in the queue. And so as long as you use a pattern where you trigger, let's say, a Lambda, and as long as the Lambda then processes that message, and then when it's done processing, then it deletes, you never have to worry about the messages getting lost. And that's a great pattern that exists with, again, a cloud native system like SQS. Also, it's important to know that Amazon SQS, the general use cases are for work queues, buffering, batch operations, request offloading, and also triggering Amazon EC2 auto scaling. So if we dive into this a little bit, work queues, what this means is that you can decouple the components of a distributed application so that they don't all have to process the work simultaneously. You can also buffer batch operations, so you can add scalability and reliability and smooth out temporary spikes because you just put the things in the queue, and then when let's say your batch instances are ready to process, they just pull them out. In fact, I built a highly available computer vision processing system for a virtual reality company a while back. And what I did was I made it so that the messages appeared in SQS, and thousands of AWS Spot instances would pull those messages down so that we could do computer vision on it. And that's really a great kind of smoothing out feature. The request offloading is something that allows you to queue the request to move the slow operations off of the interactive request path. So a great example of this for people in data engineering or machine learning engineering or ML ops would be that you have a user request, let's say some type of prediction, and the prediction involves, let's say, a Spark-based system with terabytes of data. You don't want your user interface to sit there and kind of crunch and wait for that thing to process. Instead, what you do is you would send that message into SQS. There would be, let's say, the Spark prediction system would then be triggered maybe by a Lambda, and then it would take, I don't know, let's say it takes 10 minutes. You would give the user some kind of unique ID and then maybe email them when the job is done. And then they get the result, which is a web link that they take a look at the results of their job. Right? That would be a perfect example of a scalable architecture that wouldn't block the user interface of a web page. You also can trigger the Amazon EC2 auto scaling. So SQS queues can help with determining the load on an application, especially when they're designed with the EC2 auto scaling, and you can scale up the EC2 instances in or out. Now, it's also important to know about the different types of queues. There is a standard queue, which is what I typically use, and because it has at least once delivery, but occasionally there could be more than one copy. There's best effort ordering. So most of the time the messages are ordered, and there's also basically unlimited throughput. They call it near unlimited. It's kind of like the Twitter data fire hose. You cannot consume it even if you wanted to. And there's a first in, first out queue, which is very different in that the order is guaranteed. And then in terms of the throughput, the FIFO queue, first in, first out queues, can support up to 300 messages per second. And if you batch it, it could go up to 3,000. So, I mean, 300 send, receiver, deletes per second is pretty quick, but there definitely could be scenarios where that is going to be too slow. And so you would want to carefully use that kind of queue only for things where order matters. There's also SQS has a feature called dead letter queue support, and it's a queue for messages that couldn't be processed. Another feature of SQS is this concept of visibility timeout. And so this is the period of time when the SQS will prevent other consumers from receiving and processing the same message. So this is important because you do want to be careful about not processing the same message. That could really be a mess. And so the visibility is a timeout that you can set for 30 seconds to the maximum of 12 hours. And then also Amazon has support for short poll and long poll. By default, the queues use short polling. What a short poll does, it only queries a subset of the servers based on a weighted random distribution to find messages that can be included. Amazon SQS will then send the response immediately. The contrast is that you can do long polling And this is basically sending the response after it collects the maximum number of messages for the response. A long polling makes it inexpensive to retrieve messages from your queue as soon as the messages are available. And this could reduce the cost of, let's say, SQS. The life cycle of SQS is something where you could really think about the following scenario is number one, a producer will send a message to a queue, and that message is distributed across all the SQS servers redundantly. Then when the consumer is ready to process the message, it retrieves the message from the queue. The message is being processed. It remains in the queue. During the visibility timeout, other consumers cannot process the message. And in this particular example, for example, it would be, let's say, a 40-second visibility timeout. After the processing of the message, the consumer deletes the message from the queue. This action would then prevent the message from being received and processed again until the visibility timeout expires. So this is really key when you first start using Amazon SQS, is that you have to delete the message, because in the case of a distributed system, there's no guarantee that the consumer received it, right? That's one of the core principles of the CAP theorem, right? Which is eventually consistent. So you, as the consumer, you have to do the final handshake, which is delete the message after you've received it. So a decoupling example could be, for example, an elastic load balancing system with a web tier. A customer will order something that goes into a queue. Then there's an application tier where the results are processed inside of, let's say, a primary and secondary database system. A common use case for when a queue is a great fit is a service-to-service communication. For example, a website that is a customer website, it could have a communication with the back end, and you would have the code of the front end website send messages to a queue and have the back end CRM consume them. Another example would be async work items. So a hotel booking system, if you have to cancel a reservation, this process could take a long time. So you send messages to a queue and have the same hotel booking system consume those messages and perform async cancelizations. State change. So let's say you have a service that manages resources. You could also use a queue for that. And also it's important to know when you don't want to use the SQS. So messaging has its own set of commonly encountered anti-pattern. So selecting specific messages, that's not a good fit. Also large messages. So if you're going to work with, really large messages, it's better to use something like S3 and then have a reference to the object versus the object itself being the message. So in a nutshell, Amazon SQS is a fully managed messaging queue service. It has standard support, which is essentially infinite scale, and also has FIFO, or first in, first out. A producer will send a message to a queue, and then a consumer will process it and delete the message. Messages that can't be processed are sent to dead letter queue, and long polling is a way to retrieve a large number of messages from the queue. All right, what about SNS? They're kind of similar, but in the case of pub sub or SNS here, really in a modern cloud architecture, the applications are decoupled right into these microservices. In the case of a pub sub, these publishers can put things into a topic, and you can have essentially infinite number of subscribers. These subscribers could be email, it could be Lambdas, it could be whatever. And so this pub sub pattern is very, very common for architectures. So Amazon SNS, or Simple Notification Service, is a web service that can make it easy to set up and operate notifications from the cloud. And in particular, the way it works is you create a topic, set the policies about who can publish or subscribe to that topic. The publisher then sends the messages to topics they've created or have permission to publish to. Amazon SNS then matches who is subscribed to that and then delivers the message. So Amazon SNS has encrypted topics. That's another feature. And also the durability is something that is kind of built into it as well. Although unlike SQS, they're not stored there. SNS supports the following transport protocols. So email or email JSON, these are just basically email messages. HTTP or HTTPS So you can actually post a URL, and the messages are received through an HTTP post request. There's also SMS, or short message service. There's SQS, so they can go to an SQS queue, also Lambda functions. So one little pro tip is that if you wanted to build a highly distributed Python system, what you could do is you could send a bunch of messages to a bunch of Lambdas, and that actually would be a great way to build a distributed system in Python, which itself has very poor support for distributed systems because it isn't able to handle native Linux thread support because of the GIL. So you can get around that by using the cloud as essentially an operating system itself, and SNS would then handle the concurrency for you. So you can almost think of them as a cloud thread as well. So there are many ways to use SNS, application and system alerts, pushing email and text messages, also pushing notifications. What are some things to consider? That each notification message contains a single published message. When the message is delivered successfully, there's no way to recall it. And also Amazon SNS will attempt to deliver messages from the publisher in the order they went out, but it's possible they could be interrupted. And also there's a delivery protocol. And so a few different things to remember is that there's a 4-phase retry. First, retry with no delay in between attempts, then retry with minimum delay between attempts, then retry according to a backoff model. So if you're ever familiar with that, this concept of maybe an exponential backoff function, where each time you retry, you try a little bit slower. And then finally, you would retry with a maximum delay between attempts. When the message delivery retry is exhausted, SNS can then move the message to a DL queue, or dead letter queue. SNS can use topics to decouple the message from the subscribers and also do a fan out protocol. Services like EC2, S3, and CloudWatch can publish messages to SNS. So if you wanted to do some kind of, process automation system, maybe scaling of something, you could use the SNS system really as a way to orchestrate that. So SNS versus SQS, they can be confusing. The big thing to be aware of is that SNS is pub/sub and enables applications to send time-critical messages to multiple subscribers through a push mechanism, but SQS is a send-receive paradigm through a polling method. So really they're opposite, but it's great for decoupling things. SQS provides flexibility for distributed components so they can send and receive messages concurrently. So really SNS is kind of like a fire and forget, right? Like you just throw it out there, and SQS is a little bit more robust in terms of being able to pull for things and persist the data. And it's a one-to-one relationship. Okay, let's talk a little bit about the last topic here, which is sending messages between cloud and on-prem with Amazon MQ. So what is Amazon MQ? It's a managed message broker for Apache ActiveMQ. And this enables you to set up and operate message brokers in the cloud. Message brokers enable different software systems, many that use different languages like Python and Erlang and C# and Go or whatever. And the idea here is that Amazon will manage this thing for you, which is great. And in fact, it has support for all kinds of different open standard APIs and protocols, including the Java message service, or JMS, the .NET message service, which is NMS, Advanced Message Queuing Protocol, or AMQP. I've actually used AMQP quite a bit with RabbitMQ, built huge systems actually with RabbitMQ. Especially in games, and then stream text-oriented protocol, STOMP, and then MQ telemetry transport, which is MQTT protocol, and WebSocket. So you can move basically from any message broker with the Amazon MQ, which is a pretty cool feature. Also, Amazon MQ, one of the best use cases would actually be a hybrid cloud. So you would have, let's say, a corporate data center. You would put an on-premise ActiveMQ broker, hook that into the Amazon cloud, and then you could actually have some robust communication between your cloud and the Amazon cloud. So let's break down the difference between Amazon MQ and Amazon SQS and SNS, which is a very common confusion. Amazon MQ is a managed broker service that provides compatibility with many popular message brokers. Amazon SQS and Amazon SNS are queue and topic servers, respectively, that are highly scalable. They're simple to use, and they also don't require you to set up message brokers. If you use messaging with existing applications and want to move the messages to the cloud, AWS will recommend using Amazon MQ, right? Because it has so many different open standards and protocols. But if you're building new applications, Amazon would recommend using SQS and SNS. So really, it's a great kind of transitional technology for people with their own physical data center that they need to communicate with, or maybe an application that already supports something like AMQP. All right, so really, we're done with what I wanted to cover today. And I believe what we will cover next week will be the building microservices and serverless architecture, which is one of my favorite topics to cover. So thanks again for showing up to 52 weeks of AWS. We're getting to the end here in terms of the solutions architect material. Probably after I'm done with the solutions architect material, I'm going to dive into a little bit of probably some freeform software development on AWS, give you some of my thoughts on some of the things that are happening. And then I think maybe another certification that we could cover, since I'm doing a lot of MLOps, is the AWS machine learning certification as well. So we could probably cover that in, let's say, 3 weeks or so. We could dive into preparing for the AWS machine learning certification. So thank you for everybody that showed up today, and I will talk to you soon.